Okay, in this presentation we're going to look at random variables. We have three random variables here, x, y, and z, or z if you prefer. And essentially what this presentation is about is calculations concerning variance and covariance of random variables. So x, y, and z, or z, have the same variance, sigma squared equal to 4. Okay, let's remember that. Suppose that x is independent of both y and z, and that y and z have a correlation of coefficient of rho equals 0.5. The subscript there, yz, is just to emphasize it's between those two variables, 0.5. So two key things to remember there, two calculations to get started with, or identities to get started with, okay? So we got three questions here. Calculate the covariance between y and u, where u is equal to the sum of y and z. Calculate the covariance of z and v, where v equals 3x minus 2y, and then calculate the variance of w, where w is equal to 3x minus 2y plus z. Okay, all in all, these calculations are fairly similar to each other, so just build it up bit by bit. Okay. Now, in the first instance, we're asked for the calculation of x and u. So this is the covariance, of covariance of x and u. Okay. Now, u is equal to y plus z. Okay. So essentially, this is what we're dealing with here: the covariance of x and y plus z. So what we do here is we get the covariance of. So essentially, when we have an expression like this, which is the summation of, or it's the combination of multiple terms, essentially what we do is just get the covariance of each term, and remember to keep an eye on the signs. Okay, so we have two terms here, y and z, and we want to get the correlation of y plus z with x. So essentially it's the correlation of x, the covariance of x with the first term. I should have said covariance there, not correlation. There we go. And then the covariance of x plus the second and the second term, which is z. Now we're told previously that in both cases that it's independent of both, which is to say that the covariance is 0 plus 0. Okay, that's what essentially means by independence. Okay, so 0 plus 0 equals 0. Now we'll hold on to that for later on. Okay, so we'll move on to the second part here now, and the covariance of z and what is v, which is 3x minus 2y. Again, what we do is split it up. So what I'll do here, first off, in the first instance stated as the covariance of z and 3x plus the covariance of z and 2y. Okay. Now in this instance what we can do is we can take out both expressions there, sorry, both numbers there, both constants there, 3 and 2. Okay. Now previously we were told that the covariance of z and x was, in the last question, 0. Okay, so that first part of the term there is 0. So essentially what we have to do is figure out this bit here, minus 2 times the covariance of z and y. Okay, so what we're going to do here is I have to give myself plenty of space here. Correlation of z and y equals the covariance of z and y divided by the square root of the variance of z times the variance of y. Now, in both cases, that is sigma squared equal to 4. Okay? So what we have here is square root of 4 times 4. Square root of 4 times 4 equals 4. Okay? So what we're going to do here is rearrange this expression here. So the covariance equals 4 times the correlation, okay, of zy. This is what we're told in the question, okay, which we know to be 0.5. Okay, so that's the covariance there. It's actually, sorry, I finish it off. It is 2. So minus 2 times 2 gives us minus 4 there. So that's the covariance there, that expression there. And what I have here, essentially, that's me just fleshing it out there, okay? Giving a very full description of how we do it. Okay, so the next part is, sorry, I'll just go back up here. W, the variance of W, where W equals the combination of 3x minus 2y plus z, okay? So just to be clear about something, the variance of W, here's our approach to taking it, is the covariance of W with itself, if you get me, okay? So what I'm going to do here is we have an expression here, 3x, and what I'm going to do here is get the covariance of that expression here with it, all the terms. So get the covariance with itself, which we have variance of 3x, okay? Then the covariance of 3x and 2y, or minus 2y, and then z, okay? So essentially what we end up here, this is just the first one. This is just from the point of view of 3x. We got the covariance, the variance of 3x, the covariance of 3x and minus 2y, and the covariance of 3x and z. Okay? And what we're going to do here is do this for each of the expression. So if we move on to minus 2y, okay, and then let's just start that again. 2y, and look at the second line. First off with itself, then with 3x, and then with z. So we get, well, actually, we do it in order there. Covariance of 3x minus 2y plus the variance of minus 2y plus the covariance of minus 2y and z. Okay, and so on. So we just work it through like that. Now, there is a quicker way of doing it, actually, but this is a very thorough and exacting way, but it makes it very clear what's going on. Okay. And then we do the same thing for the third line, okay? Now, so what we're going to do here is look at the... So that's how we get this expression here, okay? It's made up of 9 independent terms. Now, what I could do in the first instance is just to remark that's going to be 0, and that's going to be 0, and so on, okay? Boom. Yeah, I'll come back to that, actually. Essentially, what I'll do here is actually look at these terms first. So the variance of 3x can be written as the covariance of 3x and 3x, which is 9 times the covariance of x. Essentially take both 3's out, and then we are left with covariance of x and x, which is the variance of x. So this is where this 9 comes from. Likewise, where this 4 comes from, and this 1 comes from. Okay, so essentially what we're doing is taking out these terms here and squaring them. That's a 1 there if you wanted to consider it like that. And remember, when we square minus 2, we get plus 4. Okay, so this is what happens here. So they're all equal to sigma squared, which is to say they're all equal to 4. Okay, so this entire expression here becomes 14 times 4. So we're just going to hold on to that for a second. There's a couple of, so now the 12 minus 12 times the covariance of x and y. Let's just see how that gets gathered up. So we get it here and we get it here. And when we take out the constant terms there, 3 and minus 2, for both expressions we get minus 12, but necessarily that goes to 0 all the same. Okay, so it's minus 12 times 0, 0. Likewise, this expression here, that's where the 6 comes from, but necessarily the whole thing goes to 0 because the covariance of x and z is 0. So then we're left with this expression here, okay? And when we sort of simplify that out, we can turn that into minus 4 times the covariance of y and z. Sorry, I just realized I'm out of shot here. So I'll just, whoops. There we go. Sorry, I just realized I was out of shot there for the last one. Okay. And essentially add the two terms and then just take the scalar, the constant term out. Okay, that's all we're doing there. So that is minus 4 times the covariance of that, which is actually that should equal to 2. We got answered that as 2 in the last instance, so you don't worry about that. So it's 56 minus 8, and that is 48. Okay, so yeah, that's grand. Yeah, we'll leave it there.